square that way. Well, initially, we're not going to have that. Initially, we're talking about deterministic finite state machine, which means that whatever state we're in and whatever symbol we see will always be, whatever next character we see in the string, will be an unambiguous way to go, a deterministic way to go. There won't be any choices or questions. Later we will talk about, maybe in the next lecture, probably next lecture. There are no choices at all, so the computation is completely deterministic. Right? All right. So any questions about this example or some of the terminology that's been introduced? Or okay, so we're going to make this a little bit more formal. When we talk about a deterministic finite state machine, we describe it with a number of pieces of information. Q is a set of states that the machine has. So I'm going to M. Oh, M. Okay. Sigma, of course, is the alphabet used for the strings. Okay, so we need to specify both of those. And then you need a transition function. Okay, this is a transition function. That means if you're in a particular state and you see a particular character, what state do you next go to? Okay, so this is a function. What does it take as, I call it input, but it's a fancy mathematical term. What's the fancy mathematical term for what a function operates on? The parameter argument, or the set of arguments is called the domain? Yeah, I think it's the domain. Okay, so how do we describe the domain in the case of the finite state machine? Again, what the transition function is supposed to tell you is, based on what state you're in and what symbol you see, where's your next state? What was your next state? So what are the elements of the domain? The alphabet, well, yeah, I guess you can say that, right, because that's a symbol, right? Yeah, right, if you want to put it very mathematically, I'll write that down that way. Q cross sigma. Okay, this is what's called the Cartesian product. That means all combinations between the set Q, that's a set of states, Q is a set, and the set of characters in the alphabet. All possible combinations, all possible pairs. So this is saying a particular state and a particular character in the alphabet, and that describes the domain of this function, delta. And then the range is what? How do you describe the range of the function? The function takes a state and a character and produces what? A state, yeah. So that's a function from state cross character to state. And this is what we drew up here pictorially, schematically. If you're in state Q1 and you see a 1, then you go to Q2. Okay, this is the transition function, delta. If you're in Q1 and you see a 0, you go to Q1. That's another way of drawing out the transition function. A more, a different way, a less pictorial way, is just with a table. Q1, Q2, Q3, Q2, Q2, Q3, then 0, 1 goes to Q2. Yeah. Okay, so that's describing the transition function delta. Okay, so this is abstractly what a transition function is. This is a particular transition function that's associated with this finite state machine. Okay. So what this is saying is, whenever you want to describe a particular finite state machine, you have to describe a transition function. And the transition function is a particular instantiation of this. What is this is the delta part? It's taking pairs of states and characters and telling you what state each one of those goes to. Okay. And then what else do we need? We need Q1 with the start state. You have to specify what the start state is, and you have to specify the set of final states. Okay. So anytime somebody specifies all of these things, you have a complete description of a finite state machine. It's not necessarily deterministic. Whether or not it's deterministic, actually it is, because there's only one. This maps is just a single state. Okay. So this is a description of a deterministic finite state machine. This is the abstract specification of what it means. And anytime anybody tells you what a set Q is, what sigma is, what delta is, what Q1 is, what F is, then you have a complete description of a particular finite state machine. And you should be able to go from this description to one of these drawings. Okay? Or the other way around, you should be able to go from one of these drawings to one of these descriptions. And I'm not sure if the first homework asks you to do that explicitly, but you should be able to do that. Okay, so let's just look at a few more examples. Oh, one more thing. When you have a finite state machine, you can describe it describe it this way, and in a sense, as input to a computer, that's a full specification. But for humans, there is usually a more concise kind of way of describing what this particular finite state machine is, or what is the set of strings that finite state machine accepts. Okay? So if you look at this for a while and you think about it, what is the set of strings that this finite state machine accepts?
That's quite right. So there's not 1, 0, 1, 0, 0. This is a double string, but you can add 2 zeros.
Okay, so you're saying 1, 0, 1. Okay, well, it ends in an even number of zeros. Okay, so the ending part does have an even number of zeros here. The total number of zeros is odd, you're right, but the ending part just has an even number. Yeah.
What about 0, 0, 0, 1?
0, 0, 0, 1. Yes, well, that ends in an even number of zeros. 0 is an even number of zeros. Okay, that's what I was saying earlier was sort of the tricky part. Yeah. Okay, so I think this is right, but you have to remind yourself, remember that 0 is an even number. So if it ends in a 1, that's ending in an even number of zeros. So it has to have a 1, because in order to get over to this final state at all, it has to have a 1. And then as you're going around here, well, when you come through here, if you use a 1, you can stop. And then you're ending with a zero number of zeros. Or you go again, and if you come back to sort of the zero, since you had to go that way with a zero, if you stop at that point, then you have an even number of zeros. So whenever you stop, it's either because you just went through that way, so you're ending with a 1, or you went through this way with a 1. In most of the cases, you're ending with an even number of zeros. Or you finish with a 0. But you had to get there with that 0, so that's an even number of zeros too. Okay? Yeah, I guess you can go along there several times, not just 2 zeros, you can 4 zeros, and so on. You can make a nice proof, a more formal proof, that this is the right description of 10 to 12. Yeah, okay, fine. I thought people were getting nervous. I thought it was like we should be finishing at 10 after or something. Fine. So if you prove that this machine, the set of strings this machine accepts, what kind of technique would you use, by the way? What's what seems like a natural proof technique for this? Yeah, proof by contradiction. Okay, yeah, I'm sure you can make a proof by contradiction, and maybe I should make that like a homework problem. But there's another one that I was thinking of. Well, I only mentioned a couple of proof techniques here. Okay, that's contradiction too. Contrapositive. This one begins with I. Induction, right? And we probably adopt it on the length of the string. Okay, you want to say that this is a description of the set of strings that this machine accepts. Well, what are all the strings of length 1 that the machine accepts? Just 1 in this case. It's just the string that contains a set of 1. And that's satisfied that this contains a 1 and gets an even number of zeros. Okay? And then you say, well, suppose this is true for strings of a certain length. Now, you have a longer length and so on. So you can get an induction proof based on the length of the strings. Okay. All right, let's get to another example. We're going to get really, really familiar with... actually, but I want to introduce one more expression. There's an issue. A topological operation. So generally, if we just have a set of strings, that's called a language. Okay, so the formal definition of what a language is in this topic area is just some set of strings. Okay? And for a deterministic finite state machine M, the set of strings that M accepts is called language. And it's even written as L of M. Okay? So this triple here means defined as like a mathematical quality. For these two of these. When you have 3, it's just saying this is a definition. So in finite machine M, we're talking about L of M, that's the language that's defined by M accepts. Okay. So let's look at another finite state machine and see if we can figure out what the language that it accepts. Okay. 1, 0, 1, 2, 1, 0. Okay, so we start out, our start state is also our final state, and well, it is what it is. Let's look at some strings that it accepts. If it goes, well, it accepts 0 as a string. definitely because you can go in there. It also accepts the empty string. Empty string is usually written like a little epsilon. Okay, that's the empty string. It accepts the empty string because the start state and the final state are the same. But to put it more correctly, the start state is the final state. Okay? So that's the empty string. What about 0, 1, 1, 1, 1, 0? Accept or reject? Yeah, it accepts that one. 0, 1, what about that one? It rejects that one, yeah, okay. So now can we psychoanalyze this machine and say more concisely what is the language that it accepts? Empty string or ends in 0. Okay, so yes, it certainly accepts the empty string, and the only way to get into the final state here, other than starting the final state, is with a 0. Okay, so that seems right. So we only go in two different directions. One is to say that in your description, everything that you say that accepts it actually does accept that, and that anything that's excluded by what you describe is not accepted. Okay, so everything you said, it's either the empty string or it's a string that ends in 0, and definitely we can see that that's necessary. That it be the empty string or ends in 0, because this is the only way to get to the final state. And if it ends in something other than a 0, that's all the set of the other ones, then where are you? The only way to end with something else is to get a 1 either this way or 1 that way, in which case you're in Q2, which is not a final state. So that sort of, in a hand-waving way, is an actual proof that what you said is right. So ML is either the empty string or a string that ends in 0. Okay, now I have on my notes that it would be an interesting question to think about removing this. I don't know why anymore, so I won't. Okay, I should write down more explicitly what I mean. Okay. All right, and then actually the book makes a comment that it probably should never have got into. Here we said that the set of strings that M accepts is called the language that M accepts. Not too controversial. But then the book says, well, really, we don't want to use that language for some, we don't use those words for a particular reason. And so instead we're going to talk about recognizes. And then, if they just had said that in the beginning, then they wouldn't have to go back and make that change. So a finite state machine accepts or rejects a particular string. They want to use those words, accept and reject, when you're talking about a string. But when you're talking about a language, then the book wants to make the distinction and say that the finite state machine recognizes a particular language. Okay. All right. Okay. Then we can say a little bit more about what a computation is. Now that we've seen some finite state machines and we've seen how to describe them, what is a formal way to define a particular finite state machine? How do we talk about what a computation is? What is a computation on a finite state machine, or a deterministic finite state machine? And by the way, I should have pointed out one thing. Why is this kind of a machine called a finite state machine? Well, we've got states, okay. Why is a machine? I don't know. But finite is obvious because the number of states here is finite, and I probably should have put that explicitly. A finite set of states. Okay. Which probably never would have occurred to you that there might be an infinite. There might be machines that have an infinite number of states. Well, you can certainly conceive of them. But we aren't. We're talking about machines that have a finite number of states. So you can always write down a description of a particular machine that we're thinking about in this class. It will have a finite set of states. It's something that's writable. Okay, so what do we mean if we talk about a computation of a finite state machine that recognizes a particular language? Okay, so computation is there's a sequence of states called R0, R1 to Rn. This is a variable. There's some number of states that the machine goes through. And why is it called R and not Q? Well, okay, that's sort of a silly question. I just need to point out that we're using these Qs to talk about the specific states that are in the finite state machine. And here we're talking about a sequence of states that the particular computation goes through. So these variables R0, R1, their values will be particular states, they'll be particular Qs. But we're talking abstractly, then I need to use a different symbol. If I told you there's a sequence of states Q0, Q2, Q16, and so on, that's a specific list of states and not an abstract object that refers to the fact that there is some sequence of states. Okay, it's a very, very fine pedagogical point about the use of mathematical notation. Okay, so there's a sequence of states such that R0 is equal to equals Ri plus 1. So this is saying, this is Ri, well, I equals 0, and minus 1. So here we're talking about states that are in this particular sequence. And states, this is a sequence of ordering of those states. And so Ri comes just before Ri plus 1. Ri minus 1 comes just before Ri 1. So this is saying the transition function for this Fourier machine has to have the property that when you state Ri of that sequence, and you see character, the I plus first character in W, then this delta function should be mapping this state and this character to Ri plus 1. That's the relationship between Ri plus 1, and this character Wi plus 1. And the fact that this is an I and I plus 1, that just has to do with the subscripting here. We started with a 0 for the states, but we start with a 1 when we're talking about characters in a string. Okay? It's terribly confusing. Sometimes the first element in something is element 0, and sometimes it's element 1. But you should all be familiar with that kind of confusion because you've been programming in C, right? Or C++, where in an array, the first element is what subscript? 0. Okay? A piece of insanity that got inserted into C and other programming languages causes no other trouble. Sane people know that the first element in anything is element 1, not 0. But anyway, so here we're starting with 0 for one object. This is a sequence, but we're starting with 1 for the object is F. This is a string. Okay, go figure. But anyway, you can deal with it. So this is what it means that the computation that M is, there's a computation of, or on W, input W, is that there's some sequence of states which has this property. Okay? And then what do we mean that the computation accepts W? What does that mean in terms of this abstraction here? Yeah, Rn. Yeah, Rn is in the final states. Okay? And rejects means that Rn is not in the final state. Okay, so the distinction, this we're going to formalize here is what it means for scientific machines to have a computation. And not just sort of writing up in some mathematical way. What it means when you look at an actual diagram or a schematic of a scientific machine